Okay, so this is our project presentation for Team 45 for our SMAI project. So initially we started off to predict the EPL match outcomes. Uh, so we wanted to predict the match winner and the goal scored, and our aim was to leverage this and the bookmaker odds that we find on platforms like Bet365, and to suppose we are given a sum of money, we want to maximize profit in hopes that our odds will be better than the bookmaker odds. So that was our initial motive behind doing this. So we collected data from 661 matches from this website, which is footballdata.co.uk. We collected data from 3 seasons, EPL data 23, 24, and 25, total of 661 matches. So this is what the data set looks like. So these are the features, and we have not used all of them. We'll get into what features we've used. So we've used some like HST, AST, then B365, 365D, which are the bookmaker odds, and of course the halftime away goals, halftime home goals, final results, and stuff like that. Okay. So our initial ambition was to beat the bookmaker odds, but we found out during the course of this project that beating bookmaker odds is next to impossible, because not only are they extremely accurate, but they are also dynamic, which means that they don't remain constant throughout the game. So the bookmaker odds might start off with something, but eventually during the course of the game they'll change to the correct value. So they'll always reflect the correct value, because these are past matches data. So we made a pivot to predict the match winner and the goal scored. So we perform basic data exploration. So let's look at that first. So we installed the dependencies and we loaded the data sets into Python pandas data frames. And this is how the data looks like. So as you can see, these are the features: full time, half goals, full time, away goals, full time results, half time results, home shots, away shots, etc. And these are the bookmaker odds. So we made a basic EDA, like match outcome distribution and what it looks like. So our aim during this part was to find out correlations between features, which ones we can leverage to make the best predictions and stuff like that. So here, so far we're just doing exploratory data analysis here. These are the EPL standings. We try to find some correlation between them and the features. So here we've calculated the implied probabilities by the outcomes, and we try to find out like how accurate are the bookmaker odds. Turns out that they're extremely accurate. Okay, now here we try to get an idea of the team form. So the way we went about it initially was just for the last 10 matches, how many matches have they won, how many matches have they lost. So it's just a weighted average of that. It's a very oversimplistic model that was not ever supposed to give us accuracy, but we just wanted to see like how it would fare using a standard model. And then this is the new engineered feature that we came up with, which is the hot streak. So we felt that a team which is winning matches in a row might have more chances of winning the current match. So and also like the hot streak feature was supposed to put more weight on the recent matches than the past matches, but in this case, as you can see, it's just constant weights being allotted to the to the wins and draws and losses. So this is a very simplistic version of hot streak. Later on we have calculated a better version of hot streak using exponential decay, where the highest weight 1 is given to the most recent 2-3 matches, and the lowest weight 0 is or near 0 is given to the like the 10th match from like the last 10th match. So that's how we've used exponential decay for that, and we really thought that this would work. So we created a 10 match rolling window, where we calculated this hot streak metric, and we wanted to see, using this metric, would that give us a better prediction than the features already in place. So here we are trying to compute hot streaks for all teams. Here we have calculated the hot streaks. Okay, now let's see if the metric holds any water. So as you can see, the hot streak feature was a complete bust, because now it was turns out it's a negative correlation for these 3 teams, and even if it were like negative correlation for all teams, maybe we could have used it, but for these three teams it was negative, but for some teams it's like zero, for some teams it's like positive, so it's inconclusive. So we can't really use this to make any kind of predictions. So we are just trying out, like trying to see if why the hot streak feature failed, trying to come up with explanations, and we thought like this might be a logical flaw in the metric, uh, or like maybe it was oversimplistic. And also we realized that football is a very dynamic game, so the past matches data can never give us accurate representations of the current match performance, and a team which has been losing the last 3 matches might be more motivated to win the current match. So maybe our logic wasn't great to begin with. So then we tried to compute team state and attack strength, which are also new features, which are based on the past wins and losses only. So we are just trying to get a gauge on the current team state, like team performance, like what kind of state they're in, so that we thought that that'll help in our predictions. So the first we've incorporated that into our data set now. As you can see, these are the engineered features: team state, attack strength, and based on that we just try to train a few basic models like logistic regression, random forest, XGBoost, which are known to have good performance in these kind of data sets. So our after initial run, logistic regression gave us a high accuracy of 77.8, which is actually more than the research paper, so this indicates that extreme overfitting. Random forest gave us an accuracy of 66.7%, which is in line with the expected outcomes. XGBoost, similar performance, and then we used an ensemble model of random forest and XGBoost, but even that gave us a 0.667% accuracy, 0.667 accuracy. Then then we tried to get SVM into the mix. So SVM turns out, we really had high hopes for SVM, but it turns out that its accuracy was far lower. Okay, so this is the point where we thought like we were getting from the scores, we saw that like we were doing pretty well with the wins and the losses, but we were doing horribly for the draws. So we realized that our data set contains very few draws as opposed to wins and losses. So our model might be more inclined to classify a match as a win or loss rather than a draw. So we tried to incorporate some synthetic data into the mix. We used SMOTE, which is a synthetic which adds synthetic data. So even with that, our accuracy didn't improve much. As you can see, like in our random forest model, just a second. Yeah, so the accuracy is pretty much the same. Yeah, so the draws hasn't improved a lot. Then yeah, so we tried to engineer another feature called goal margin differential. So the goal margin differential, we thought like it places heavy weight on like matches where one team was completely wiped out by another team. So we thought like if in the past few matches a team has completely annihilated another team, maybe that team is like far stronger in a much better state. So maybe our predictions will be better if we incorporate that into the mix. But as we found out later, it didn't. I mean, it increased the draws percentage by like a few decimal points, but not like appreciable enough. As you can see, the draws has increased from 0.29 to 0.33, but the recall is still the same. F1 score is pretty much the same. So overall, not great. Like it didn't help much, at least not as much as we had hoped for. So after that, we decided to stick to our features so far, like the attack strength and the other engineered features that we, except for the hot streak, because that's like of no use. Then we tried to see like which feature our models were like prioritizing on. So as you can see, like the highest feature importance is for halftime goals and away halftime goals, which is to be expected. Then since we had already incorporated the betting odds, we were concerned that whether we were parroting the betting odds, in the sense that was our model too heavily reliant on the betting odds? Were we just parroting whatever the betting odds predicted? So we tried to do a analysis of that, like um, somewhere there. But we realized even though our model was predicting, like our model correlated strongly with the betting odds, even without the betting odds, even if we didn't include the betting odds into our data, it was giving similar, maybe not the same, but like similar results. So which proves that like our model is not that dependent on the betting odds feature. So far whatever we've done, we've concatenated into one single cell here. Like this trains the models, saves the model in a folder, and computes all the features that we discussed, and finally trains the models and saves them in this folder called models. And then we have the evaluation. Evaluation is very simple. So we we load the models and the data from the stored weights, and then we run a series of tests. Our performance, we evaluate performance using the metrics root mean squared error, MAE, and R squared loss. So these are our results. This is the classification report and the regression matrix. This is not amazing, but at the same time it is to be noted that on this data set even the research paper was unable to get a bit better prediction. These are the final feature importances for full-time home goals and full-time away goals. Yeah, and for our inference, we've used this is a very simple piece of code where we just loaded a model, tested it on some data. In this case, that being like a few teams, but we've tested with just one team, Arsenal versus Man City. So the regressor model, the random forest regressor model, gives us a home goals of 2.36 and away goals of 1.25, which is close to the actual score. The predicted winner in this case is correct, but again, like this only works for like 65, 60, 70% of the cases. So in some cases, especially for like outliers, like where there are like 5 goals or like 7 goals scored in a match, the regression model doesn't fare that well. So coming back to our slide, we've performed satisfactory data exploration and feature engineered. We tried to do as much as possible using the current data sets, and we tried to augment the data set by thinking of ways to improving our predictions by incorporating new features. And we discussed hot streak and goal margin differential were 2 of them, and the attack strength feature was also another one of them. So we used SMOT and then regression models like we discussed. Our primary model was random forest regressor because the logistic regression model was definitely overfitting on the training data. So yeah, we decided not to do the bookmaker prediction betting thing because it's just a knapsack model. So it reduces to like if you're given an X amount of money, which bets should you place to maximize your profit. Since our predictions are always in alignment with the bookmaker odds, it didn't seem necessary to actually make that because anybody can do that. Like, so that was not something that would be novel. Deliverables, we have already delivered on our report, all the code, all the model data, and our plots. The plots folder is consists of yeah. So we have stored all the necessary whatever exploitative data analysis and the regression models gave us. We've plotted confusion matrices, odds versus outcome, prediction distributions, residual errors, everything, and saved them into this folder. As you can see, the true positive and true negatives far outweigh the false positive and false negatives, which is, I mean, the false positive, false negatives are not very low, but that is to be expected from this kind of data set. So this is under plots, and everything we've uploaded in our Moodle as a project and in the respective subfolders as mentioned. That's about it from my end. Thank you.